As a corollary of the previous theorem, we obtain this: if A and B are relatively prime, then there exist integers s and t such that as plus bt is equal to 1. Relatively prime means that the GCD of A and B is equal to 1, and then we just apply the theorem. The GCDs can be written as a linear combination of the numbers A and B. Euclid's lemma: if P is a prime that divides the product of two integers A and B, then P divides A or P divides B. Proof: if P divides A, we don't have anything to prove. The conclusion is true. So let's consider the other case. P doesn't divide A. Our goal is to prove that P divides B. Since P is a prime, the GCD of A and B is 1. And there exists integers s and t according to the corollary, such that 1 is a linear combination of A and P. Now multiply this with B, this equality with B, we get this. Here P divides the product, so P will divide this number. How we know? It is given in the problem in the beginning. P divides AB. So P divides the first term. Obviously P divides the second number, and hence P will divide the sum, but the sum is B. So P divides B, and we complete the proof. Theorem, the fundamental theorem of arithmetic. Every integer greater than 1 is a prime or a product of primes. This product is unique except for the order in which the factors appear. That is, if n is written in two ways as a product of primes, p1 times p2 times pr, and the second way q1 times q2 times and so on qs, where the p's and the q's are primes, then r and s are equal. The number of primes is the same in both products. And after reordering the q's, we'll have the corresponding p's and q's equal. We defined least common multiple here. The least common multiple of two non-zero integers A and B is the smallest positive integer that is a multiple of both A and B. We'll denote this by LCM of A and B. And the fundamental theorem of arithmetic gives a convenient way of finding the LCM and the previously defined GCD. So if we want to find the GCD in the LCM of two numbers, we first write them as a product of prime powers, and then to find the GCD, we go over the primes and try only those primes that appear in both numbers, in the factorization of both numbers, and we write the prime at with exponent the smallest of the two. For example, 2 appears in both numbers. Here it appears with exponent 3, here with exponent 4, so I take the smaller one. For the next number, 3, it appears in the second factorization, but not in the first, so I don't write 3 in the GCD. The next number is 5. It appears in both the same exponent, so we write 5 squared. 7 cubed appears here, and 7 to the 4th appears in the first number. The smaller one is cubed, so I write 7 cubed. And this way you obtain the GCD. The LCM is handled similarly, but instead of taking the smaller exponent, we take the larger one. 2 appears in both factorizations. We write 2 to the 4, the big one, in the LCM. 3 squared appears here. We don't have 3 here, but we can think that it is 3 to the power 0, and 0 is smaller than 2. So we write 3 squared. 5 squared, the bigger one is the second power, 5 squared. They are equal, so it doesn't matter which one you'll take. 7 cubed, 7 to the 4, 7 to the 4 is bigger. So this is the LCM. This rule applies if we find the GCD, if we want to find the GCD of not just 2 but 3 numbers or more in the LCM. So let's find the GCD of 26, 56, and 72, and the LCM of these 3 numbers. First we factor them. 26 is 2 times 13. 56 is 8 times 7, and 8 is 2 cubed. So 2 cubed times 7. And 72 is 8 times 9. 8 is 2 cubed, and 9 is 3 squared. And then we apply the rule. 2 appears here, here, and here in all of the 3 numbers. And the smallest exponent is 1. So I write 2 to the first, just 2. 3 squared, no 3, no 3. So no 3 doesn't go in the GCD. The next prime, 7. 7 appears here, not here, not here. 7 doesn't go in the GCD. The next prime, 13. It appears in the first, but not in the second and third. So the GCD of these 3 numbers is just 2. The LCM, we again go over the primes, but this time we pick the largest exponent. 2 to the first cubed. the largest exponent is 3. So 2 cubed appears in the LCM. The next prime, 3. 3 squared, no 3, no 3. The largest power of 3 is squared. The next prime, 7. 7 in the second number, no 7 here, no 7. So the largest power of 7 is the first power. It goes in the LCM. And the last prime is 13. In the first number, no 13 in the second, no 13 in the third. So the largest power of 13 is the first power that appears in any of the numbers. So this is the LCM. And if you want, you can multiply out, but it is more convenient to keep it as a product.